Hello dear friends, welcome to a lecture on ring theory. Today in this lecture we shall study homomorphism of rings. We shall define what is homomorphism, then we shall state some results regarding homomorphism, and also we shall define kernel of homomorphism. Then we shall see some examples of homomorphism. Now homomorphism, as we have studied in group theory, two groups are said to be homomorphic if there is a structure preserving property. Here also for ring theory there are two binary operations, addition and multiplication. So therefore the homomorphism of two rings is defined. Here is the definition I have written: a mapping phi from the ring R into the ring R dash. It is a mapping function which is denoted by phi from one ring to another ring R dash or R prime, and this is said to be homomorphism, is called homomorphism if for A and B belongs to R, these two properties are satisfied. Actually these two properties are known as structure preserving properties. Structure preserving properties for addition and multiplication. Now, so what is the first property? Phi of A plus B is equal to phi of A plus phi of B. That means phi image of addition of two elements is equal to addition of their phi images. And similarly, phi image of multiplication of two elements is equal to multiplication of their phi images. If these two properties are satisfied, then the mapping is known as homomorphism of the two rings. And now we shall see results regarding this homomorphism. Phi is a homomorphism of R into R dash. Then first result is phi of 0 is equal to 0. This 0 is in R. This is identity with respect to addition, and that is 0 element of R, and this 0 is the 0 element of R dash. Sometimes it is denoted by 0 dash, but here we have simply denoted by 0. That means identity is mapped to identity under homomorphism. And the second result is phi of negative A, additive inverse of A, and is equal to additive inverse of phi of A, phi image of A. And that means additive inverse is mapped to additive inverse here. So this happens for every A belongs to R. Now these are easy to prove. See, the first is we have for A, see 0, that is phi of A plus 0. We can have phi of A plus 0 for A belongs to R. And what is this from the first property, that is phi of A plus B is equal to phi of A plus phi of B, and this is phi of A plus phi of 0. But what is the left side? And this is A plus 0 is again A by property of 0. This is equal to phi of A plus phi of 0. And you see what this shows. This shows that phi of A is equal to phi of A plus phi of 0 means phi of 0 is the 0 element of R, and therefore or additive identity. So phi of 0 is the 0 element of R dash. The images are in R dash, and that means if it is a mapping between one ring R to another ring R dash. This is phi mapping, and here is 0 is the 0 element of R, and that is mapped to phi of 0. Phi of 0, which is 0 element of R dash. So, but we have not denoted by 0 dash, we simply denoted by 0, but this 0 is in R dash. That is the first property. Phi of 0 is 0 element of R dash, or therefore phi of 0 is equal to 0. Now the second, what is the second is phi of minus A, negative A, is equal to negative phi of A. And to prove this second result is also easy. We can write phi of a plus of minus a, phi of a plus of minus a. And again using this property, we have this is phi of a plus phi of minus a. And but what we have here is phi of a plus of negative a, that is phi of 0. Phi of 0 is equal to phi of a plus phi of negative a. And you see this phi of 0, by first property it is 0. 0 is equal to phi of a plus phi of minus a. And what this shows, if their addition is 0, these two are additive inverse of each other. And therefore phi of a and phi of negative a are additive inverses. Additive inverses in R dash. And that means phi of a is equal to negative, or this phi of a is equal to negative of phi of a. Phi of minus a is equal to negative of phi of a for all a belongs to R. And this proves the second result, let a belongs to R. So that means a is here, then its image is phi of a, and there is negative a and its image is negative phi. So these are the two simple properties of homomorphism. Identity is mapped to identity and additive inverse is mapped to additive inverse of the element phi of a. Now we shall define what is kernel of homomorphism. And that is our next definition. If phi is homomorphism, of ring R into R dash, another ring R dash, then the kernel of phi denoted by this I of phi is the set of all elements A in R such that phi of A is equal to 0. So this is the definition of kernel A, or that is kernel of phi we have defined. Again see, phi is the homomorphism from R to R dash, and it satisfies these two properties, or that is kernel of phi, that is I of phi, is equal to those elements A belongs to R such that their image is equal to 0. A belongs to R such that phi of A is equal to 0. And certainly this 0 is in kernel because its image is equal to 0. So 0 element of R dash. This phi of A is equal to 0. This 0 is the 0. Images are in R dash, and therefore this 0 is a 0 element of R dash. And thus this is in the kernel, 0 is in the kernel, and we will write simply 0. So if there are other elements whose image is 0, then all these elements will be in kernel. So that means there is another element which is mapped all to 0. All these elements are mapped to 0. Then this is kernel. This is if every element of this is mapped to 0, then this will be, this set is known as kernel I of phi. So the set of elements whose images are equal to 0, then that is known as kernel of this homomorphism and denoted by I of phi. Now we shall prove a result related to kernel. That is our lemma. If or phi is a homomorphism, again homomorphism of ring R into ring R dash, then first thing is first result. Here also we will prove two results. First, kernel of phi, I of phi is a subgroup R under addition. And second is, if A belongs to kernel of phi and R belongs to R, then AR and RA belongs to kernel of phi, R in I of phi. For every if A belongs to kernel of phi and R belongs to R, then AR and RA are in kernel of phi. I of phi is kernel of phi. We have used this notation. So we shall prove this. What is kernel? We have defined just as this is a homomorphism from R to R dash, and kernel of this homomorphism is the set of all the elements A whose image is equal to 0. So therefore this is kernel. These we are supposing that every element in this set is mapped to 0, and therefore this will be kernel of this homomorphism. It is a, and what we have to prove, this is subgroup of R under addition. Obviously this is subset of R. I of phi is subset of R. Now what we are required to prove is subgroup under addition, and to prove it is a subgroup under addition, we need to prove two things. It is sufficient to prove it is closed under addition and the additive inverse exists under addition, and the additive inverse exists for this I of phi, then it will be a subgroup. So we shall prove it now. So this is the definition of kernel phi. We have to remember, it is easy. I shall write the definition here. I of phi. I of phi is kernel phi, and that is A belongs to R such that phi of A is equal to 0. And now you see, the first, this is the definition of homomorphism, which is important. We are using this to prove the results. And now the proof of the lemma. First part. To prove I of phi is subgroup of R under addition. So we shall prove I of phi is closed under addition and additive inverse exists. Exists for every element in I of phi. So these are the sufficient conditions for a subgroup. To prove a subgroup, we need only two things to be proved. It is closed under the operation and its inverse exists under that operation. Now here we have to prove that it is a subgroup under addition, means it is closed under addition, that we have to prove, and for that closure property we have to prove. For this purpose, let A and B belongs to I of phi. What we have to prove? A plus B also belongs to I of phi. And what this implies? This implies by definition, therefore phi of A, if an element is in kernel, in this kernel, its image is 0. So therefore phi of A is equal to 0 and phi of B is equal to 0 by definition of kernel. See, and now what is phi of A plus B? Phi of A plus B, by definition of homomorphism, phi is homomorphism, and therefore this first condition, both the conditions are satisfied. According to the first condition, this will be phi of A plus B is phi of A, structure preserving property for addition, phi of A plus phi of B, but both are 0 because both are the elements in kernel, and therefore its image is 0, 0 plus 0, and again 0 plus 0 is 0, and thus what we have? Phi of A plus B equal to 0, means A plus B is also in the kernel. So therefore A plus B belongs to I of phi, the kernel, and this shows that A and B belongs to kernel, their addition also belongs to kernel, means I of phi is closed under addition, therefore is closed under addition. Now second, the additive inverse exists. Further, so this is to be proved under addition, and now let A belongs to I of phi. Let A belongs to kernel of phi, and this implies phi of A is equal to 0. It is in kernel, so its image is 0. Now phi of negative A, and this just we have proved in earlier lemma, that is phi of negative A is equal to negative of phi of A. This we have proved, and that is but what is phi of A? That is 0. So negative 0 is again 0, and therefore this phi of negative A is also equal to 0, and this proves that therefore negative A belongs to kernel of phi, and thus every element has additive inverse. Therefore every element in I of phi, every element has additive inverse. In I of phi, and thus this proves I of phi is a subgroup. So that we have proved. Now second property, so I shall write the statement here, that is therefore I of phi is a subgroup under addition, subgroup of R. This is subset of R and satisfying closure and additive inverse. Therefore it is a subgroup of R under addition. Now the second property, this is to be proved. What is the second property? I shall write the proof here, proof for second, and that is easy. See, if A belongs to I of phi and R belongs to R, then AR and RA both are in I of phi, kernel of phi. First thing is, let A belongs to kernel of phi, and therefore this implies phi of A is equal to 0. Now let R belongs to R, then phi of A into R, that we shall consider. Phi of A into R, now we shall use the second property of homomorphism, structure preserving property of homomorphism. Phi of AB is equal to phi A into phi B, and this will be phi of A into phi of R, and both are in A is also in R because I of phi is subset of R, and therefore this property can be used, and this is equal to, what is the phi of A? 0 into phi of R, and we know that 0 into any element of a ring is again 0. So also what this shows, AR belongs to kernel because its image is 0, and therefore, or you can write also phi of RA, phi of R into A, and that is by the same property is phi of R into phi of A, and this is phi of R into 0. We don't know what about R. R is any element, its image is written as again phi of R, but we know phi of A is 0 because A is in the kernel, and therefore this is 0, and thus image of both AR and RA is 0, and therefore these are the elements in the kernel by definition of kernel. So thus AR and RA are both in kernel of phi. So this proves the second result also. So thus we have studied the definition of homomorphism, which has these two properties, and we have seen kernel of this homomorphism, and also some results regarding this, that is kernel is subgroup, and the element, if A is in kernel, then RA and AR also are in kernel. Now we shall see some simple examples of homomorphism. See, first simple example we shall consider as let R and R dash be any rings, any arbitrary rings with corresponding operations of addition and multiplication. We define phi, that is homomorphism from R to R dash, by phi of A is equal to 0 for all A belongs to R. Then this phi is a homomorphism. Then phi is a homomorphism known as zero homomorphism, or phi is a zero homomorphism. See, it is easy to verify these two properties. So what about the first property, A plus B, that is. So what is the meaning of this mapping? Phi of A is equal to 0 for all A. Every element of R is mapped to single element 0 of R dash. Here 0 is, that means all the elements of this R are mapped to this 0. So if we denote 0 element here, then every element of this first ring is mapped to 0 and no other. It has the single image, every element has the same image. And thus what about the first property? We have phi of A plus B. For A, B belongs to R, we have phi of A plus B is phi A plus phi B. But phi A and phi B both are 0 because every element A, B, C, etc. are all mapped to 0. This is the definition of the mapping, and therefore this is equal to 0 plus 0, which is equal to 0. First, and that proves the result, that is this is equal to phi of A plus B, and this is also 0. 0 is equal to phi of, or by definition this is 0. 0 is equal to phi of A plus phi of B, and that is phi of A plus B. Each element is 0. This is 0, this is 0, this is 0. 0 is equal to 0 plus 0, and that proves the first. What about the second? Phi of AB, that is also 0. A into B is again an element of R, closure property. AB is there, so this is suppose AB element, that image is also 0. So that is phi of AB is equal to 0. also phi of A into phi of B, that is 0 into 0 and that is 0, so both are equal, and therefore phi of AB is equal to phi A plus phi B, phi A into phi B, and therefore this is homomorphism, which is known as zero homomorphism. And second easier example we shall consider as, or that is also simple example. Let R be a ring and let R is equal to R dash. Let R is equal to R dash and define phi. Define phi from R to R dash by phi of x is equal to x for all x belongs to R. Then this is also a homomorphism, because these properties are easily satisfied. So since we will have what is phi of A plus B, by definition every element is mapped to itself, image is the same, and therefore phi of A plus B is equal to A plus B, and that A can be written as phi of A by this definition, and this B is phi of B. So therefore phi of A plus B is equal to phi of A plus phi of B. Similarly, phi of AB is equal to AB, and that is phi into phi, and therefore both these properties are satisfied for AB belongs to R, and thus this is also an example of homomorphism. And the next example can be considered as, let J root 2 denote the set of real numbers A plus or I may write A plus B or M plus N root 2, where M and N are integers. And that means J root 2 is equal to the numbers, real numbers of this type, M plus N root 2, M, N are integers. And then this forms a ring under addition and usual addition and multiplication. Then J root 2 is a ring with usual addition and multiplication. You may verify this, it is easy to verify. There are 8 axioms of ring theory. You refer earlier examples of ring, definition of ring and examples of ring, and according to that you see that these lectures, and similar to the earlier example, we can prove the closure property for addition, associative property. There is additive identity, that is 0 plus 0 root 2, and other properties can also be proved easily. So this is a ring, and we define a mapping. So first the two structures are ring structures are to be considered, and then a correspondence or transformation between two rings is to be defined, and then that forms homomorphism if it preserves the structure under addition and multiplication. We define this as phi a mapping from ring J of root 2 to J of root 2, same ring, by phi of M plus N root 2 is equal to M minus N root 2. M, N are integers, and M plus N root 2 belongs to J of root 2. So this is a homomorphism, example of homomorphism. And how to verify these two properties? See, phi of A plus B, two such elements are to be considered and their addition, and this is single element M plus N root 2. So two elements we can consider for two elements we will have like this. Phi of first element we can consider m1 plus n1 root 2, and second element we shall consider m2 plus n2 root 2 of this type in J of root 2. Every element of J of root 2 is of this having two parts. First is integer plus second is integer multiplied by root 2, and therefore two such elements we have considered in this way. And there is addition, usual addition, so therefore this will be phi of these integers are added m1 plus m2 plus, and then these are added together n1 plus n2 root 2. And by the definition of this, so what is the image? Image is considered as this the addition becomes subtraction, or the negative part of the second element, second part, its additive inverse, and therefore this becomes negative m1 plus m2 minus n1 plus n2 times root 2. And now this we can bifurcate as m1 minus n1 root 2 and plus m2 minus n2 root 2. And you see this is what is phi image of m1 plus n1 root 2 according to this definition, m1 plus n1 root 2, and this is phi image of m2 plus n2 root 2. And thus this proves the first property of homomorphism. A plus phi of A plus B is equal to phi of A plus phi of B. So phi of the addition of two elements is equal to addition of their phi images. And similarly the second can also be proved. So that is, second is phi of the multiplication of these two, m1 plus n1 root 2, or we may use this type of bracket, m2 plus n2 root 2, and it is usual multiplication. This is a ring under usual addition and multiplication. So therefore what is the multiplication of this? m1 m2 plus this product n1 n2 into root 2 is 2 n1 n2, and plus now root 2 can be taken common, and we have m1 n2 plus m2 n1 times root 2. You may check it, and this is equal to phi of phi image of this is equal to, by definition, that is the first part m1 m2 plus 2 times n1 n2, negative of this m1 n2 plus m2 n1 into root 2. Now it can be written as a product of these two. See, m1 minus n1 root 2 and m2 minus n2 root 2. We can check it easily. m1, the product of this m1 m2 plus this negative into negative becomes positive, and this first part, and second negative sign is common, and then if you take negative sign common, then and root 2 common, then m1 n2 and m2 n1, and negative sign is common. So but what is this? This is phi image of m1 plus n1 root 2, and this is phi image of m2 plus n2 root 2. So thus phi is, so this satisfies the second property. Phi of A into B is equal to phi A into phi B. Phi of multiplication of two elements is equal to multiplication of their phi images, and thus phi is a homomorphism. So thus we have studied some examples of homomorphism. For homomorphism, two properties are to be satisfied, and then it becomes mapping between two rings, which is known as homomorphism. So I hope you may understand this the homomorphism and its examples. The remaining part we will continue in our next lecture. Thank you for watching this lecture.